all HOD departments, faculties, and the other participants who present here. I am Ayushi Singhal, Head of the Physics Department, wants to welcome you all here for the FDP program. As we all know, we are gathered here for the second day of FDP program. Yesterday already I mentioned about the FDP, but in the detail, sir will also guide you. And FDP today is the second day session. The morning session will be taken care by our NRI principal, Dr. Puran Gaur sir, and sir has a 24-year plus experience, and the topic will be the qualification of IoT devices for semiconductor manufacturers. So please come on the podium and please have a look here.
Thank you. Today is the second day of FDP program. So now I am Dr. Puran Gaur from NRI Institute of Science and Technology, Bhopal. So today we have to deliver the title is the propositions of IoT devices for semiconductor manufacturing. So first of all, we know what is the IoT. IoT is Internet of Things. And then we have to use the many applications. It is the home devices, commercial purpose, vehicle, and many applications for the daily life we are using the IoT. And for IoT, what we have to do? We have to require the sensors, different type of the sensors, and that sensors we have to discuss here, and how do they fabricate it by using the different material that today we have to discuss here. I have to discuss here, and how they are fabricated and how to implement it, and for the different substrate also, and that we have to discuss here. So for the next slide. Yeah, before going to this, we have to discuss about the what is the antenna designing by using the IoT in higher frequency. That is the terahertz. You know about the terahertz? What is the frequency range of the terahertz? 12. Okay, that is the 0.1 terahertz to 10 terahertz. Some papers we have to use here for discussing about the our topic. Before going to this, discuss some PhD work we have to done already by using the FR4 substrate. These are the substrate generally we have to use for making the antenna. This is the gallium arsenide. Generally we are using the two types of substrate here, low temperature gallium arsenide and semi integrated gallium arsenide to fabricate that. Generally we are using the design FR4. These are the antenna we already fabricated by using the FR4 for the 10 GHz. These are the long threading antenna. These are the 10 GHz antenna which is fabricated. This is the aperture covered antenna, which is already designed by using the SMA connector, and they are connected by using the dielectric substrate, that is the FR4. We know the permittivity of the FR4 is 4.4. And we use the any type of substrate for designing of the antenna. Generally we use this wood also. But only the thing is that we have to use the layer of the copper layer and front end and the second end copper layer. So and by using the stuff matching, we fabricate this of the antenna. This all of the antenna designing by the FR4 substrate. copper clad is the front side and second side is the copper side, and this both the end are connected by using the SMA connector, and then these SMA connectors are connected to the network analyzer, and by using the network analyzer we testing the frequency of the antenna. Okay, so these are the things. And that's all. These are the base paper generally we using to describe here. Here, the fabrication is by using the semiconductor materials, that is the gallium arsenide, anti-gallium arsenide, and second one is the Si gallium arsenide, and that are separated by the Bragg reflector that is designed by using the aluminum AI, and the second one is the AU. This is the designing here. See here, this designing is here. SI, semi-integrated gallium arsenide, and anti is the low temperature gallium arsenide. This antenna designing by using this substrate. Okay, here is the this one is acting. These two is acting as a ground. Here the some material is added, that is the aluminum arsenide and gallium arsenide. This is called as the reflector. This is called as the reflector. This is fabricated by using this semi-integrated gallium arsenide. Okay, and this total antenna is the photoconductivity antenna. Photoconductivity antenna. This fabricated by the silicon nitride. This is the actually mica. Generally we are using the mica. Some of the person is the from chemistry. So that is used by the mica. And these total semiconductors are generally used for the terahertz frequency. And these fabrications is defined by the some equations. That equation is come by the Maxwell equations. Okay. So the width and length of this material is fabricated by using the Maxwell equations. Okay, that is the first, second, third, and fourth. So these materials are generally used by the semiconductor, but here we are using the silicon, only the silicon. Okay. So these two materials are separated by this Bragg reflector. Okay. Generally, what happened for any type of the antenna, we have to require the reflections of the electromagnetic wave into the free space. That is known as the fringing field. Okay, and that antenna is required for some supply from the external device, and that external device we use the network analyzer, and that is connected to this SMA connector. And this one is the SMA connector which is connected to this copper plate is known as the ground plate. Okay, and second one is the reflector and exciting pad, and this is separated by the dielectric material, just like as a capacitor. We are using the two capacitor. One side is the positive plate, second one is the negative plate. Okay, and that is separated by the some dielectric material. That dielectric material is dependent upon the distribution of the charges. Okay, so here we have to using the finite ground plane. Suppose if we are not using this patch here, so they are act as a infinite ground plane. We know this soil is also a reflector, an electromagnetic wave reflector. Same as here we have to using the conductor. This is the form of copper. Okay, so this is act as a perfect reflector of the electromagnetic wave. Okay. According to this, we have to using the stump matching technique, and this different type of the cutting we know here. These are the different type of the cutting is there. They are cut by using the stump matching technique. है ना, that is lambda by 4. If I use the lambda by 4, है ना, lambda is wavelength, है ना, that depend upon the frequency and velocity of light. We know the lambda equal to c by f. What is the c? C is the velocity of light, and it is the value, and its value is 3 that is for 8 meter per second. And f is the resonant frequency in which type of frequency is required to transmit the signal into the free space. And that defines the lambda. And what is the lambda? Lambda is defined the total wavelength that contains the plus cycle, positive cycle and negative cycle. Okay, 360 degrees here. Okay, according to that, we have to match the impedance of the source load. And for the maximum power transmission, what we have required? Load impedance equal to maximum power transmission source impedance. है ना? Yes or no? ठीक है, source impedance equal to load impedance, and that is comes into the lambda by 4 for step matching technique. And in lambda by 4, conductors are connected in parallel with capacitor. Conductors are connected with parallel with capacitors. And if conductors are connected with capacitors, then they are act as a oscillators, tank oscillators. You know the tank oscillators. है ना? And without applying the what is the oscillator? Without applying anything, we have to get the oscillation at the output side. And but the thing is that the capacitor is charging position. Okay, so if we have to capacitor is charge connected across the inductors, what happens? The capacitors are discharged through inductors. And what is the property of the inductors? They oppose it cause. So if the capacitor is discharged through the inductors, they oppose it cause. If the capacitors are charged in this way, suppose capacitor is charged in this way, then what happens? They oppose the cause. Suppose this is the positive cycle, they are charging exponentially and discharge exponentially. Okay, suppose they oppose it cause, then what happens? They become negative and this one becomes positive. So in this way, we have to get the sinusoidal. Okay, so they have come by lambda by 4. This technique is called as the step matching technique, and according to that step matching technique, we have read the slot of the straight edge. Okay, why we have to do this? Because we have to transfer the maximum to maximum way into the free space. Okay, and then the second point is come. All these things are come according to this one. That's why I am telling you. Here they are using the LT gallium arsenide, and second substitute is Si gallium arsenide. But these materials, this thing is not fabricated. We require some reinforcement. This is the spiral antenna. This one I have to give the patent. I have to assign the patent of this spiral antenna. They are published, but not yet granted. But we have to try to grant the patent. This is a spiral antenna. In that case, we are using the two metal, and that is separated by the tiny film. But here it is separated by the air. This is the spiral antenna, this is the sub-refractor, or this is the main refractor. Okay? If we have connected the voltage to this one, the maximum signal is transmitted to free space. Some of the signal are reflected to this one and then reflected back to the free air. So that is known as the frilling field. This is the another antenna, spiral antenna. Okay? This is one type of the also antenna that is a short backfire antenna. This is we use this antenna by navigation purpose. They are connected in seat. If आपको जानते हैं कि the seat is going to the outside of the city and so far distance from the city. At that time they have not to use the heavy antenna. For that purpose, they using this short backer antenna. This is the tested antenna, or we have to this one is granted by the design pattern. This is already published in the design pattern. Okay, so this antenna is generally used for the seat purpose, for the navigation purpose, and this antenna is operated for C band 4 to 8 to 12 gigahertz, S band and C band. S band and C band 8 to 12 gigahertz and 4 to 8 gigahertz. Microwave frequency. But we have to go for the terahertz. Right now we have to go for the terahertz. That is generally used for the IoT application and for 6G applications. So these are the different antennas, and one type of the antenna is also here. That is the long traveling antenna. This is the aperture coupled microstrip antenna. You have to see here in between two, one gap is there, that is the air. Okay? They are operated by the mutual coupling. If you want to see that, see. These are operated for the infrared ground plane. Infrared ये हम बिल्कुल चीज देख रहे हैं, तो we have to work on the hand-ons also, है ना? ठीक है? तो ये जितनी भी चीजें हैं, they are designed by me itself, है ना? ठीक है? और these all antennas are having the different applications, है? And right now we have to go for the IoT purpose. One antenna is also in there. That is the hexagonal same antenna. This is operated for the 6 gigahertz. 6 gigahertz frequency. This antenna is also designed. This antenna is designed by the students. Only students. Okay. So this one is generally used. So our basic concept is there. This one is using the material low temperature gallium arsenide and silicon integrated gallium arsenide. These two designs are generally used for the IoT application. One paper is also here. This is the value of the. We have to see here that this is the data sheet of the gallium arsenide, low temperature gallium arsenide. That is the 500 nanometers, and the permittivity is of this antenna is 12.9. What is the permittivity of this antenna is 12.9. For the any antenna designing, we have to define the resonant frequency and the permittivity of the antenna. So we know the low temperature gallium arsenide permittivity is 12.9. Okay. So these things we have to know, and this antenna is operated by terahertz, that is the 0.1 to 10 terahertz. Okay. So these are the different things generally we have to discuss in this paper. Another one, this one is the paper. This is designed by the three university. These, Gaurav, Akash, Dinesh, Purnima, Sharma and Varun Yadav. Department of Manipal University, Department of Electronic Communication, DLA University, and Department of Analytical for Manipal, Academy of Higher Education, Manipal, Karnataka. So these same papers here we have to, I have to design. This is the design for the terahertz frequency. This is the design for the terahertz frequency operations. This is used for the rover. Which material we have to use? Rover. The different materials are available, but this material is not available in subject. So many antennas are designing here for the FR4 subject. यहाँ पे जो भी डिजाइन किया है, they are only for the simulated purpose, not design the hardware part. They not design the hardware part. They only design and simulate the design. But we have to go for the hardware part also. ठीक है, तो अगर यहाँ देखेंगे दे नॉट डिजाइन द ओनली दे शो द वन VSWR result but not go for the hardware part. See here is any hardware part? No, है ना? ठीक है, तो these are the different data sheets. These are the different data sheets for according to the nanometers, है ना? 0.6 nanometers data sheets here, है ना? So these are the different data sheets. We have to see the yesterday the CM Roy sir is asking about the different material that is fabricated by using the that is fabricated for CMOS, है ना? So these are the that thing is here, है ना? And what kind of the data is required for that sheets, that is also given in this data sheets, no? Generally what we have to require, we have to only the required here is the permittivity of the material, है ना? According to that we have to design the antenna, है ना? First of all antenna or sensor, what we have to here discuss about the sensor, which type of the electromagnetic wave is sent by the antenna, that is discussed here. Okay, so these are the different geo design, है ना? So these are the generally actually these designs are designed by the me, है ना? For silicon material, which material? Silicon material. Okay, so what frequency generally they have to use the 0.1 terahertz to 10 terahertz, है ना? So 0.1 terahertz to 10 terahertz generally the frequency for the 6G application, है ना? Recently the 6G applications are not implemented, but right now we are going for the 6G application, and that 6G application, what is the use of the IoT, Internet of Things, है ना? So that thing we have to discuss here and design the one antenna for IoT applications. Okay, so see here, these are the previously what they had to do, that was discussed here. Okay. This design generally will be used for IoT applications. So the size of this antenna is very miniature. These papers are generally used for designing, and generally we have to use that paper that is designed by the gallium arsenide, low temperature gallium arsenide and semi-insulated gallium arsenide. Here we only use the silicon material and then separated by 1.5 in between the two silicons and then fabricated. These are generally the software which the antenna is to be simulated, है ना? ठीक है, HFS, है ना? These are the softwares, different softwares that the antenna is to be simulated, है ना? Then according to that antenna we have to design, है ना? These different frequency, these are ruler, these are the materials, and an embedded photonic crystal, these all are the materials, FR for substrate, and FR for substrate. ठीक है, these different materials are generally used to fabricate the antenna. ठीक है, रॉगर इज नॉट अवेलेबल हियर, है ना? फोटोनिक वी हैव रिक्वायर्ड द सम, जैसा अगर हमें कुछ फोटोनिक्स में मटेरियल्स को इंटीग्रेट करना है तो रिक्वायर्ड द सम रिसोर्सेज, बट नॉट अवेलेबल हियर, है ना? दे आर अवेलेबल इन IISc बैंगलोर, है ना? So we go for the IISc बैंगलोर, है ना? And then fabricate that thing with the IISc बैंगलोर. ठीक है, then this is the bandwidth in which bandwidth they are operated. Here it is written here that 24.5 gigahertz to 29.5 gigahertz. What is the bandwidth here? 29.5 minus 24.5 gigahertz. So that is the bandwidth. In that bandwidth, the antenna is to be operated. Similar here, 63 gigahertz, 44. This is the percentage. How to calculate the percentage here? Fh minus FL divided by Fh plus FL divided by 2. मतलब 2 multiplied by Fh minus FL divided by Fh plus FL. है ना? The percentage to be come. Okay? ठीक है? In this way, है ना? What is the return loss? What is the return loss? Generally, all the parameters of the antenna is calculated by using the scattering parameter. You know the scattering parameters? Scattering parameters means how much the power is transmitted and how much the power is reflected by 4 points. Generally, here we use the percentage. This is only having the one pole. In that pole, we have to transmit it and reflect it only the single pole. But how much the transmitted signal is received by the another side, we don't know. And that is calculated by using the network analyzer. That is Agilent company that is designed by the network analyzer, and then how much transmitted by this and how much the received by the same pole. So that thing is tested by the Agilent instrument. Agilent network analyzer. Okay. तो अब यहाँ से कितना power, how much the power is transmitted by this pole, है ना? That is measured by the scattering parameter. That is the S11. है ना? What is the 11 is here? Yes, one pole transmitted and one pole reflected back in this pole. है ना? That is the S11. है ना? ठीक है? And then S12. Second one is the S12. Suppose here S11. One is transmitted, this is the transmitted, and one is how much the reflected back from the load side. Okay, this is the S11. Suppose if you are taking the S12, one is transmitted, and second how much the received the signal from the port 1. Okay, in this way we have to transmit the parameter, and that parameter is known as the return loss. Okay, and how to calculate the return loss? 20 log 10 phase minus PR divided by power transmitted. है ना? ठीक है? तो they come the reflection. है ना? And this is generally come by the minus 10 dB. Minus 10 dB. है ना? Minus 10 dB. So that signal is come in below that minus 10 dB. That signal is to be calculated. है ना? So that's why the maximum return loss here is minus 30 dB. Here is minus 60 dB, minus 50 dB, minus 29 dB, and minus 22 dB. In this way, we have to calculate the return loss. So what problem we have to identify there? है ना? So here the different problems identified, है ना? For terahertz IoT applications. First one is the VSWR is less than 2 होना चाहिए, है ना? Identification. But here the VSWR is more than 2. है ना? What is the VSWR here? What is the VSWR? Voltage standing wave ratio. Voltage standing wave ratio. And its value is equal to 1 plus rho or 1 minus rho. What is the rho here? Rho is the reflection coefficient. What is the rho? Rho is the reflection coefficient. है ना? And what VSWR is to be identified कि how much power is transmitted from the load side. है ना? अगर हम कोई चीज ट्रांसमिट कर रहे हैं तो रिफ्लेक्ट होना चाहिए क्या? रिफ्लेक्ट होना चाहिए क्या लोड साइड के साथ, सोर्स साइड के साथ? नहीं होना चाहिए. व्हाई? अदरवाइज जो हम सोर्स है दैट इज द डैमेज, है ना? ठीक है, तो मैक्सिमम पावर इज ट्रांसमिटेड टू द लोड साइड, है ना? दैट्स व्हाई वी हैव टू कैलकुलेट द मैक्सिमम पावर ट्रांसफर. मैक्सिमम पावर ट्रांसमिशन, है ना. तो मैक्सिमम पावर ट्रांसमिटेड, है ना, एंड हाउ मच पावर इज रिफ्लेक्टेड बैक टू द लोड साइड. ऐसा पॉसिबल है कि मैक्सिमम पावर ट्रांसमिट हो जाए 100%? नो, है ना. तो सम पावर इज रिफ्लेक्टेड बैक टू द सोर्स साइड, है ना. दैट इज कैलकुलेटेड बाय द VSWR. That is calculated by the VSWR, है ना. And what is the value of the VSWR here? 0 to infinite, 0 to infinite, है ना. 0 to infinite. If there is no reflection, then what is the reflection coefficient equal value is 1. What is the reflection coefficient value is 1. So what is the value here? Infinite. Yes or no? है ना. So the value of VSWR is ranging from 1 to 2. It is the unit place device. It is the unit place. है ना. Sometimes it is calculated as Vmax by Vmin. Vmax by Vmin. है ना. Vmax by Vmin. V मतलब voltage maximum divided by voltage minimum. है ना. Okay. So that is known as the VSWR, and its value is always less than 2. है ना. Always less than 2. Okay. The next is axial ratio. What is the axial ratio? अगर हम कोई भी एंटीना का वैल्यू पोलराइजेशन अगर हम क्रिएट कैलकुलेटेड, then at that time we know the axial ratio, है ना. अगर we know the antenna, there are the two angles. One is the azimut angle and second one is the elevation angle. One is the azimut angle and second one is the elevation angle. This is denoted by the azimut angle is denoted by the phi and it is denoted by the theta. Only the two field is there. First one is the electric field and second one is the magnetic field. है ना. ठीक है. Suppose we have the different type of polarization generally, and vertical, horizontal, and elliptical, circular. These are the different types of polarization. You can transmit something into the free space, है ना. ठीक है. अगर हम कोई फील्ड को ट्रांसमिट करते हैं into the free space, they are the different types of polarization, है ना. वो या तो vertical हो सकता है, horizontal हो सकता है ना. ठीक है. elliptical हो सकता है, circular हो सकता है ना. That thing is defined by the these two angles, phi and theta. Okay, and that is denoted by the axial ratio, and axial ratio is nothing but E theta divided by E phi. E theta divided by E phi, है ना. अगर हम कह रहे हैं कि both are the equal, then वैसा ये रीडिंग वाले बता सकते हैं if both angles are equal, E theta by E phi, if two angles are this is ratio, है ना, and both angles are equal, then what happens? Equal. Both angles, suppose both are the ratio, है ना, and both angles are equal, then which type of the polarization is there? Which type of the they are creating the straight line, vertical line, and what polarization they are creating? Semi circle means parabola, है ना. मतलब which type of the angle they are creating? The elliptical angle, है ना. Which polarization is there? Elliptical angle, है ना. So in this way they are, if this is equal to 1 means both are the equal, है ना. If they are 0, it is not possible. 0 मतलब कुछ होगा नहीं, है ना. Both are the 0. So this axial ratio is defined the polarization. Generally we are go for the two types of polarization, linear polarization and circular polarization, and this is denoted by the 3 dB. 3 dB. Agar suppose the axial ratio is less than 3 dB, then they are circular polarization. If they are more than 3 dB, then they are linear polarization, है ना. ठीक है. Yes or no? है ना. ठीक है. जनरली 0.75 अगर हम कट ऑफ बोलते हैं तो व्हाट इज द एंगल इज देयर? 3 dB, है ना. ठीक है. तो हम 0.7 एक मार्जिन लेके चल रहे हैं. इफ दे आर लेस देन 3 dB, they are circular polarization. If they are more than 0.75 dB या फिर dB they are dangerous to aviation. ठीक है, तो they define the actual ratio. ठीक है, a properly designed antenna first signal loss must be low for proper matching between the lines of the device. Secondly, the actual ratio bandwidth of the antenna must be broad as possible. है ना, तो actual ratio bandwidth जनरली हम यहाँ पे पर्टिकुलरली बैंड होते क्या है, व्हाट इज द बैंड, देयर आर डिफरेंट टाइप्स ऑफ बैंड, एल बैंड, एस बैंड, सी बैंड, एक्स बैंड, है ना, का बैंड, के बैंड. ठीक है, जैसा हम कह रहे हैं कि एल बैंड इज जनरली ऑपरेटेड बिटवीन द 1 to 2 गीगाहर्ट्ज, एस बैंड 2 to 4 गीगाहर्ट्ज, सी बैंड 4 to 8 गीगाहर्ट्ज, एक्स बैंड 8 to 12 गीगाहर्ट्ज. These are the different bands in which we have to operate the different signals. जैसे हम सुनते सैटेलाइट कम्युनिकेशन जियो, जियो मीन्स जियो अर्थ ऑर्बिट, है ना, जियो अर्थ ऑर्बिट, दे आर ऑपरेटेड 4 to 8 गीगाहर्ट्ज, 4 to 8 गीगाहर्ट्ज, 6 सी बैंड ऑपरेशंस, है ना. जैसे हम कह रहे हैं कि हमारा एक रेडियो बैंड है, जनरली व्हाट इज द रेडियो बैंड इज देयर, व्हाट इज द रेडियो बैंड फ्रीक्वेंसी, 88 to 108 मेगाहर्ट्ज, है ना. रेडियो में देखते हो ना, इनकी फ्रीक्वेंसी 96 है ना. एंड देन व्हाट इज द अदर 100 में कौन सा होता है, तो दे आर रेंजिंग फ्रॉम 88 to 108 मेगाहर्ट्ज, है ना. ठीक है, सेम आवर फ्रीक्वेंसी इज आल्सो हियर. व्हाट इज द आवर फ्रीक्वेंसी, ओमेगा की फ्रीक्वेंसी कितनी है, 20 किलोहर्ट्ज, 20 to 20 किलोहर्ट्ज, है ना. These are the different types of frequency. All human beings having the different frequency. And what is the frequency? Number of cycle per second. Number of cycle per second. एक सेकंड में कितने साइकिल ट्रांसमिट हो सकती है. अगर फ्रीक्वेंसी नहीं हो जाता तो जाएगी क्या, है ना. तो all the signal which is transmitted into the free space is having the some frequency, है ना. ठीक है, and that frequency is calculated is in the band, is in the band. So that's why I have seen here the band. जैसा मैंने कहा ह्यूमन बीइंग का बैंड क्या है, अभी बताया था 20 किलोहर्ट्ज, है ना. रेडियो का मैंने बताया 88 to 108 का, है ना. ठीक है, इस तरीके से और ऊपर भी के सेवन का बैंड. जैसा मैंने कहा जियो, एक्चुअली फॉर द सैटेलाइट ऑपरेशन दे आर थ्री टाइप ऑफ ऑपरेशन, जियो 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 जियो. नाम सुना है क्या आपने, है ना. फॉर द डिफेंस पर्पस लो अर्थ ऑर्बिट का जनरली वी आर यूजिंग मोर देन 10,000 सैटेलाइट इज देयर, है ना. मीडियम अर्थ ऑर्बिट, है ना. Then geo is covering all the earth, only the 3 satellite is there. And what is the distance from the 36,000 kilometers from the orbit of the earth, है ना. Okay. So for that purpose, geo purpose, this C band generally used, and for the playment only. Then next is transmission line model. Generally, in this antenna, we are using the two types of model. One is the cavity modeling, and second one is the transmission line modeling. And in cavity modeling, they are become a difficult. Why? Because in cavity modeling, the capacitance loading is generally required. अगर आप कोई चीज को cavity करेंगे तो then the charges transmission is required the more complicated here, है ना. But is in the transmission line model, है ना. Transmission line model they have not required any charging. Both are the connected in series, parallel, series, parallel, series, parallel. This way the signal is to be transmitted. So this is the transmission line model का, है ना. ठीक है, they are directly connected to the ground and reflected side, है ना. They not required any cavity, है ना. और this is ऐसे में connectors आप मार्केट में जब ऐसे में कनेक्टर लेने जाओगे, they required they are which type of the impedance matching will be required for the ऐसे में connector. So this is the 50 ohms matching purpose, है ना. जैसे हम कहते हैं कि रेडिएशन रेजिस्टेंस, व्हाट इज द रेडिएशन रेजिस्टेंस. सपोज अगर हम सिंगल डायपोल की अगर बात करते हैं, सिंगल पोल की बात करते हैं, सिंगल पोल एवरीथिंग इज इन देयर, द मेटल इज देयर, मींस दे आर एंटीना, है ना. इफ इट इज द सप्लाई, अगर आप देखे होंगे पहले की टीवी में ऐसे सिंपल यागी का एंटीना हम यूज करते थे, हम क्या लगा देते थे, वायर लगा देते थे, एंड देन दे कैच द सिग्नल. यस और नो. अगर हमारे पास मोबाइल में अगर कुछ नहीं आ रहा तो हम क्या करेंगे, एक एंटीना में वायर लगा देंगे, दे कैच
Means every metal is having the antenna. But the thing is that we have to require the dimension for that, and what is the frequency generally we have to use for that antenna, है ना? अगर उस पर्टिकुलर फ्रीक्वेंसी को हमें पता चलता है कि उस पर्टिकुलर फ्रीक्वेंसी में अगर हमें कोई चीज बारे में आइडिया है कि हाँ यस दिस एंटीना इज यूज्ड फॉर द पर्टिकुलर फ्रीक्वेंसी, तो फॉर फ्रीक्वेंसी एंड द मटेरियल ऑफ द एंटीना कोई भी एंटीना हम डिजाइन कर सकते हैं, बट द थिंग इज दैट वी नो द फ्रीक्वेंसी एंड परमिटिविटी ऑफ दैट मटेरियल, है ना? ठीक है, तो ये चीज है। तो हमने कहा 50 ओम। अब हम कहा जा रहे हैं कि रेडिएशन रेजिस्टेंस के बारे में देखते हैं। रेडिएशन रेजिस्टेंस इज द कॉम्बिनेशन ऑफ रिएक्टिव रेजिस्टेंस एंड रियल रेजिस्टेंस। अगर हम रेडिएशन रेजिस्टेंस की बात करते हैं, रेडिएशन रेजिस्टेंस मस्ट बी रियल पार्ट, ओनली द रियल पार्ट, है ना? और सिंगल डायपोल्स का इसका जो रेडिएशन रेजिस्टेंस होता है दैट इज कम टू द कैलकुलेशन, दैट इज द 80 पाई स्क्वायर L स्क्वायर डिवाइडेड बाय 3 लैम्डा, है ना? दिस इज द सिंगल पोल एंटीना। एक सिंगल वायर को ले लो, है ना? द रेडिएशन रेजिस्टेंस ऑफ दैट इज 80 पाई स्क्वायर L स्क्वायर डिवाइडेड बाय 3 लैम्डा, है ना? अगर हम बोल रहे हैं कि रेडिएशन रेजिस्टेंस ऑफ दैट पोल, तो दैट इज द 75 ओम। दिस ऑल आर द कैलकुलेटेड, है ना? तो इन दिस वे, है ना, इन दिस वे वी गो फॉर द ट्रांसमिशन लाइन मॉडल। ठीक है, so that transmission line model is used for the mathematical analysis। जैसे मैंने mathematical analysis किस तरह से कैलकुलेट करते हैं, that transmission line model is used the dimension of the packs are fixed along the length of beat, the field or the edge of the packs under the fringing means what is the fringing here? The maximum signals are transmitted into the free space, that is known as the fringing। Our role, what is the role of this antenna? Antenna or sensor for the IoT purpose, what is that? The maximum field is transmitted into the field transmit होगी तभी तो हम सिग्नल को रिसीव करेंगे, अदरवाइज रिसीव करेंगे क्या? यहीं पे सरफेस अगर करंट था, यहीं पे सिग्नल एब्जॉर्ब हो गया तो सिग्नल ट्रांसमिट होगा क्या? है ना? The signal transmitted to the free space, what we have required that? What at purpose? Required the impedance matching. Required the impedance matching, है ना? That's why we are asking about the radiation resistance, है ना? तो radiation resistance जैसे हमने कहा 75 ओम, है ना? तो 50 से 75 ओम में अगर हम कोई चीज मैच करते हैं तो मैक्सिमम पावर ट्रांसफर कहाँ पर होगा? इनटू द फ्री स्पेस। ओके, तो समझ में आ रहा है? यू गेट इट और नॉट? हाँ, ठीक है। तो दैट थिंग इज देयर, है ना? द इलेक्ट्रिक फील्ड line in the antenna mostly go into the substrate, even a bead out of the substrate into the air। सेम थिंग मैंने असली कहा कि जो भी सबस्ट्रेट अगर हम ले रहे हैं, है ना, सपोज वी हैव टेकन दिस सबस्ट्रेट इज F4, है ना, एंड वी हैव टू डिजाइन दिस एंटीना फॉर 50 ओम रेडिएशन रेजिस्टेंस, देन द मैक्सिमम पावर इज ट्रांसमिटेड टू द फ्री स्पेस, है ना? ठीक है। अब सपोज द रेडिएशन रेजिस्टेंस इज ट्रांसमिटेड टू द फ्री स्पेस, है ना, फ्री स्पेस, तो उसकी वेलोसिटी ऑफ लाइट किस तरह से निकालोगे? और टू कैलकुलेट द वेलोसिटी ऑफ इलेक्ट्रोमैग्नेटिक फील्ड टू द फ्री स्पेस, that is is equal to 1 upon under root epsilon u, epsilon u। अगर फ्री स्पेस में अगर बोल रहे हैं कि 3 to 10 पर 8 मीटर पर सेकंड आ रहा है, कैसे आ रहा है? हाउ टू देखो 3 to 10 पर 8 मीटर पर सेकंड कैसे आ रहा है? That is equal upon the permittivity, relative permittivity and relative permittivity, है ना? That is 1 upon under root 8.831 into 10 to the power minus 12 multiplied by 4 by into 10 to the power minus 7, है ना? If you have to multiply this one, then you have to get the 3 into 10 to the power 8 मीटर पर सेकंड। तो कोई भी सबस्ट्रेट की अगर हमें उसमें इलेक्ट्रोमैग्नेटिक फील्ड अगर ट्रांसमिट करना है, तो then we have to know the permittivity of that substrate। हम एक वुड को भी ले सकते हैं, वुड को भी हम एक एंटीना बना सकते हैं, है ना? फाइबर को भी हम एंटीना बना सकते हैं, एक क्लॉथ को भी हम एंटीना बना सकते हैं। व्हाट इज द वेयरेबल एंटीना? वेयरेबल एंटीना इज नथिंग बट अ पॉलिस्टर, है ना? पॉलिस्टर में हम क्या कर रहे हैं? वी हैव टू वेटिंग द प्लेट, कॉपर प्लेट, कॉपर साइड 0.1 mm की शीट्स आती है कॉपर, वी हैव टू कनेक्ट इट बोथ साइड, है ना, बोथ साइड, एंड देन दे बिकम द एंटीना। गेट डिजाइन है ना? अगर आपको देखना तो मैं वो भी दिखा दूंगा, हमने वो भी बनाया है ना? तो the next one is the epsilon effective. Epsilon effective. These epsilon are effective. Take the तो क्वेश्चन जो भी आप पूछ सकते हो, देखो ये बहुत ही इंटरेस्टिंग है। हर चीज में हमें एंटीनास की रिक्वायरमेंट है। इससे एंटीना देखो, हम जब भी मोबाइल में भी हम एंटीना यूज कर रहे हैं तो ये लोग ऐसा कर रहे हैं। बाहर के अंदर में एक डबल साइड का एंटीना होता है जो उस पर हम एंटीना के साथ सेव होता है, ठीक है। तो हर एक में मल्टीप्लायर होता है। जब हम ऑप्टिकल फाइबर बोलते हैं, ऑप्टिकल फाइबर में डायमीटर के बाद रिपीटर लगता है, तो सेम एंटीना का एक वाले में रिपीटर्स है, रिपीटर्स हर जगह रिपीटर्स है। विदाउट रिपीटर नो, इसकी रेंज कितनी होगी? 5 मीटर 10 मीटर पर, इससे ज्यादा। हम वॉकी टॉकी जो यूज करते हैं, जो एंटीना यूज कर रहे हैं वो सेम है ना। एवरी देखिए, एवरी एंटीना के बाद रिपीटर्स रिक्वायर्ड है। पहले एंटीना आपको याद होगा, रेडियो पे कितना ऊंचा लगता था, टावर, सबसे बड़ा टावर जिसको रेड है। लेकिन आज पॉसिबिलिटी है, आज कम लोग, क्योंकि एंटीनास हर साइड में रिपीटर है। जैसे आप यहाँ पे तो ओरिजिनल में देखोगे आपको डबल साइड का एंटीना आपके एंटीनास के इसमें लगा होगा, है ना। तो हर डायरेक्शन में एंटीनास को टीच करने के लिए रिक्वायर्ड है।
फ्रीक्वेंसी यूज कर रहे हैं।
हाँ,
हाई फ्रीक्वेंसी यूज कर रहे हैं, बैंडविड्थ बढ़ गया है। ये कवरेज एरिया है।
और कुछ सही क्वेश्चन था, और कुछ मैं पूछ सकता हूँ।
Shape is also defined. Shape of the antenna is also defined.
Shape of the antenna is also defined the bandwidth parameter. Generally, what we have required here, we require the maximum to maximum bandwidth for the different applications. जैसे हमने कहा wireless applications, WMAX, है ना। So that we have required different broadband. कि इस ब्रॉडबैंड में सब चीज इंक्लूड हो जाए, तो इसमें मोबाइल भी आ जाए, वाईमैक्स भी आ जाए, लैन भी आ जाए, WLAN भी आ जाए, है ना। फॉर दैट पर्पस में डिजाइन में डिफरेंट है ना। एंड दैट इज डिफाइंड बाय द सेम। जैसे आपने कहा नॉट कटिंग है, सेम कटिंग, है ना। सेम कटिंग इज जनरली व्हाट वी डू फॉर द λ/4, है ना। लैम्ब्डा कैसा निकलेगा? वी नो द फ्रीक्वेंसी, रेजोनेंट फ्रीक्वेंसी, बीच फ्रीक्वेंसी यू हैव टू यूज फॉर द ट्रांसमिशन एंड रिसीव सिग्नल, है ना। अगर वी नो द λ/4 lambda, then we automatically define the term measure, है ना। क्लास में है किसी
Last first lecture.
बंद करो।